Welcome everybody, panelists and attendees. This is the 2020 edition of Next Generation Electrochemistry. This is a program that's been running now in its 5th year. Every summer, this has funding from the National Science Foundation, and the ECS is very kindly sponsoring our event, and we'll be hosting this video once we're done with all the panels. And this is administered out of UIC. My name is Jordi Cabana from the Department of Chemistry at UIC. And I'm the director of the program. George Crabtree, who happens to be in the call too, is the co-director. So this is the first time that we're doing NGenE with this structure. Normally, this is a 1-week workshop where we have lectures and we have attendees that are physically in the room. So it works almost like a class. Because of the pandemic, we had to cancel the physical version, and we decided that instead of not running anything, that we would do a condensed version only online. And instead of having lectures, which are kind of passive, that we would have panel discussions to make it a little more interactive, because one of the tenets of NGenE is that there's interactivity and there's a lot of discussion. So we're running 4 panels today and tomorrow. This is the first one, Frontiers in Energy Storage. We've been going since 10, solving some technical issues. We have another one in the afternoon on integration of computational and experimental approaches, generally in electrochemistry. And that'll run at 1 p.m. Chicago time, Central Time. And then we have 2 more tomorrow, again at 10. We're covering topics that are a little more new to the field of electrochemistry in a sense, because they're getting just now a lot of prominence. One is electrochemistry at the water energy nexus, and the other one is organic electrochemistry, which is not a very new field, but it's gaining a lot of visibility in recent years. If you're in this call and you want to attend the other panels and you haven't received information, please contact Thomas. You should have his email. I'm not going to put it here because he's going to go in a recording and I don't want to dox him. Contact him and ask him for information. Everybody who's in this call, panelists and attendees, is welcome to be an attendee in the other panels. And we're hoping that all the attendees actually attend all panels, just like the attendees of NGenE stay with us for the whole week. So the plan of the panel is that this is meant to be an unstructured discussion. There's no significant script. Just minimize this thing. The composition of the panel is the best of the best and the best of the brightest of the field for each topic of the panel. To kind of get going, not that the people that are participating need a lot of incentive to get going, but we'll go around and have a 5-minute opening statement on what they think are the key fundamental questions on the topic that we're discussing in each panel. In this case, it would be energy storage. And because this is a program on electrochemistry, I've instructed that they try to think about how those questions relate to electrochemistry per se, more than, how to commercialize something. After the 5-minute opening statement, there'll be discussion. And this is driven by the panelists, but at that point, at that moment, we'll start looking at the chat to see if the attendees, who are a selected group of students and postdocs, want to start asking questions. So it can start right away. In NGenE, we've had lectures that were almost entirely driven by student discussion. We're trying to live stream this event through YouTube, where hundreds of people have actually asked to access. We're having Zoom and YouTube having issues talking to each other, which we're trying to solve. But if it works during the webinar, we'll go live stream. Otherwise, we'll figure it out for the other panels. We have 90 minutes, and so we'll stop at 11:30, or we have a tentative stop at 11:30. The discussion is going. We don't have anything else until 1, so there's always an option for some people to stay in the webinar if they want, and if that's the case, I would stay too. I am going to be the moderator. So for the faculty, this is what I say every year for NGenE, so it applies here. The philosophy of this program is not to think about what's been done, but to really think hard about what we don't know. And, you know, this is not a paper that we're trying to publish. We don't have to pretend that we know all the answers. It's the opposite. We want to particularly highlight things that we don't have an answer to. Controversy is good as long as it's polite. So, because, you know, the things that we don't know may be controversial. So feel free to, you know, make the floor uncomfortable. And remember that you're talking to the next generation of scientists. And so this is an opportunity to, you know, influence thinking in the field beyond the people in each of your groups. Share your wisdom. How do you think critically? How do you connect things to electrochemistry? That's what we're looking for. For the attendees, we want you involved. It's not as spontaneous as it is physically. Those of you that have attended, some of you are alumni. It's a lot easier to be interactive when you're live in the same room. Don't let that stop you. Please use the chat of Zoom when you have a question. Type something there. I'm monitoring the chat. That's most of what I'm doing. And I'll give you the floor as soon as I see you say something. And after that, we'll open your mic. Right now, you don't have mic privileges, but you'll get mic privileges if you have a question, and you'll keep them until your question is answered adequately, basically. So don't be afraid to challenge what you're hearing. Ask difficult questions. The people in the panel, I know them, they love difficult questions. And then absorb as much as you can out of these panels that you're gonna hear. Think about it also in the context of some of you are thinking about careers in research in electrochemistry or industry. Think about how all of this is gonna play in your career. Okay, so that's my opening statement. We agreed before we started the call that we would go around the room in a given order, and each panelist is gonna share the screen. So we have 4 attendees. We have Stan Whittingham from Binghamton University. He'll go first. Then George Crabtree will go after him. He's at Argonne National Lab and University of Illinois, Chicago. Then it'll be Héctor Abruña, who is at Cornell University, and right now he's also at the beach. And we'll have then Clare Gray, who is from University of Cambridge. So we have the luxury of, because we're online, of having somebody from across the pond. And she will close out the opening statements before we start the discussion. Like I said, panelists, please try to stay to 5 minutes so that we can have a lot of discussion. And Stan, whenever you're ready, go ahead.
Okay, I'm ready. Welcome, everybody. I thought it'd be useful to show a little bit of history because I think there's no one in the audience amongst the students who were around when lithium-ion batteries first came on the scene. So on the left-hand side, I'm showing here 2 lithium-ion batteries from the 1970s. The upper one is still working. It's in my office. So a good lithium-ion battery lasts forever. Below that is a lithium-ion battery used in Chicago in 1977 at a large EV show. And you can see this original ideas then have led to all these applications on the right-hand side. And I show you 2 Peterbilt trucks. These are probably the largest electric vehicles available today. The 16-wheeler there is now in the Los Angeles dock, moving the large devices from the ships to local distribution centers. And then there's the garbage truck, which is again an ideal application for electric vehicles. So it's moving into everything. At the bottom here is showing the what the UK ambassador did last December. She was pushing electric vehicles hard, and if you see there's a nice Jaguar on the left, and on the right-hand side is a London taxi, both all electric. So next time Claire's in London, she can drive in an electric taxi. But the area where I want to emphasize more is renewable energy. Both the sun and the wind shine and blow when they feel like it. So we need a large amount of storage to make those work. So we need storage to enable renewable energy. So the next slide here really shows a bit of a push that we older folks owe the next generation better environment than we presently have. And if you look at what the coronavirus has done, the one positive thing it maybe it's cleaned the environment. We need to take advantage of it and not go back to the old normal. I'm sure we've all learned there's a lot of things we can do from home. We don't all need to get on the plane to have a battery meeting one every week in the year. And to push that, you'll see on the right-hand side, there was an announcement in Le Monde earlier, a couple of months ago, signed by saying, let's not go back to the old normal. So I see some of the figures, we are going back there. What batteries will do is allow us to electrify the society, both for generation and transportation. And at the bottom there, there's a message from Akira Yoshino, John Goodenough, and myself, what we said at the banquet speech again, pushing that lithium batteries have now been recognized, now we owe it back to the field. So let me just point out a few things in the last slide, which some, I think, interesting things. In the United States, in April, more electricity was generated from renewable sources than from coal. I think in the US, there'll probably be no new coal plants built because renewable is now a lower cost than coal. This is mostly because there's minimal cost during operation. You don't need staff, and the fuel in the solar or wind plant is free. So you don't have to buy coal, oil, or gas. There is a slight complication to that in the sense that you can't necessarily turn the wind or the sun off, so it will generate even if you don't need it. According to BBC, it's now more than 3 months since any coal was used for generating electricity in Britain. So that's another big plus, though I understand Germany and others are building new coal power plants. The real electrochemical challenge in my mind is we need sustainable and recyclable batteries. The present ones are not all that recyclable, so we need new science. We've got to eliminate toxic materials, and I use toxic in the broadest possible sense, both poisonous and child labor issues. So we really need to get cobalt out. We need to remove the NMP from the manufacturing. We need to ideally get rid of the flammable electrolytes, and we need to get rid of fluorine-containing materials in the battery. So this includes the binder and the electrolyte, because those result in fluorine gases and liquids, which are causing a real problem in recycling plants. And the other thing I request of everybody is reduce the hype in your publications. Great science doesn't need to be hyped, and hype doesn't help us in Washington. And I'll stop there. Thank you all very much, and wait your questions later.
All right. Thank you, Stan. So next
share.
would be, yeah, if you stop, then George, you're next.
Yeah, thanks very much. Let's see if I can get my screen up. Where is it? Here we go. I hope. Can you see anything? Not yet?
Not yet. There you go. It's coming. Yeah, it's there.
Okay, and we'll put it on full screen. Yeah, so thanks. Welcome, everyone. I'm George Crabtree, as Jordy said. Stan gave a great introduction, and I'm going to say some similar things, actually, the two slides that I have. One is to take a look at this slide. The battery, of course, is right in the middle of this slide. We all understand the electrochemistry is there. But there are two things, in addition to the battery, the applications on the right-hand side and the raw materials supply chain on the left-hand side. And as we've learned with lithium ion, Stan was pointing this out, you can't focus only on the electrochemistry, although this, of course, panel will. But in the larger picture, you have to look at the applications. So one point I'd like to make for everyone to keep in mind is that the application determines which batteries will be successful. And this is well proven by the present generation of lithium ion, which was designed specifically in 1991 to power a camcorder that Sony wanted to bring out. Needed a smaller, higher energy density battery, and lithium ion was the choice. It was had twice the energy density of the next best battery, and kind of made the camcorder a success. So that's the first example of the application selecting the battery. Now we have many, many more applications, again, as Stan was saying, for transportation. An EV battery is about 10,000 times bigger than the battery in your laptop or your cell phone. It's a very different animal. It has a whole different set of performance specs that it must satisfy in order to be successful. And it looks like it's launched on the path, at least for personal cars, of being successful and being the next generation of transportation. Stan was showing some trucks. That's a little farther behind personal cars. There's also maritime shipping on rivers and across the ocean, and freight trucks. And we're starting to see these become electrified as well. The next step would be aviation, and you see that at the top of the screen on the right, airplanes. Lots of talk about that, and it really looks like a rich area too, and that will require a very different kind of battery. As Stan was pointing out, it's the grid that has to become renewable and sustainable and carbon-free. So the two circles and the transmission lines in the center between those two circles represent that. There are many applications on the grid for batteries, backing up wind and solar, for which you need batteries that can discharge for maybe 3 or 4 days in a row, because that's how long a cloudy period or a calm period can last. Lithium-ion batteries cannot do that. They can discharge for about 4 hours or 6 hours maybe, but not much more. It just gets too expensive. So we need long-duration batteries. And it's those applications that we ought to be looking to when we develop the next generation of batteries. On the left-hand side, the raw materials supply chain, and Stan also mentioned this, cobalt is the poster child, a problem for child labor reasons and also for just coming from one country and can be rather expensive. The supply chain often limits what kind of battery will be successful. So what we're looking for are batteries that fill new, very compelling applications, one of which is EVs right now, and there's several beyond that, including aviation and shipping, trucking, and ones that have very simple supply chains. So the lithium-ion battery supply chain is rather complex. We need to recycle. That's not on this graph, but that takes the right-hand side back to the left-hand side, and that's another area for science. So the point of this slide is at the bottom in the yellow, the ecosystem consisting of supply chain, battery, and application develops as a whole. You can't develop, say, just the electrochemistry and expect to be successful. Last slide here, this is a bit of an advertisement for J. Caesar, the organization that I direct. It's said in words on the left and in pictures on the right. Let's just look at the pictures. The idea is to build the battery from the bottom up. So start with atoms, start with molecules. Atoms and molecules can be put into crystals. These crystals and molecules are the building blocks for making the battery. What do we need? We need transformative materials, chemistries, and architectures. That is things we don't have now. So that means beyond lithium ion, that will give us the batteries that have the performance metrics to satisfy the applications, i.e. electric vehicles. Lithium ion batteries actually can do. They're not the best suited for it, but they can. But there are many applications where lithium ion won't work. So the idea of J. Caesar is to do exactly that, to build from the bottom up. This is something that we could not have done 10 years ago because we did not understand the atomic and molecular level origins, electrochemical origins of battery behavior well enough. Now we're beginning to. So we can design where every atom, every molecule has a prescribed role in producing a given battery performance metric. If there's some molecules and atoms there that are redundant that you don't need, get rid of them. If you need to put something in that gives you a performance metric, put it in. And this, I think, is the goal across the community, and certainly the goal of J. Caesar. The idea is that we'll take these transformative materials, chemistries, and architectures and mix and match them to produce the batteries that are designed for the application. Many of those applications are still emerging, so we don't quite know what the performance metrics are required for those applications to succeed. But when we understand it, we'll have the transformative materials, chemistries, and architectures to do that. So that's the end of my slides. Happy to take questions later on, as Dan said. Let me try to stop. Let's see.
Thanks, George. It's in the, if you go to the top, it'll be. Yeah.
Yep. Okay.
Héctor, are you ready? Uh-oh, Tito has disappeared. No beach. Oh, there you go. Okay. You're muted.
Can you hear me now?
Yeah.
Excellent. So let's see. Let's go here. So this is where we are. Thanks for everybody for attending. It's a little bit peculiar, but this should be a boatload of fun. This is the NGenE for 2020. Basically, shameless propaganda for the EFRCs that were responsible for the work that I'll be talking about. So if we look at the design criteria, what do we need? And so here on the left, so we want infinite energy. Remember, it's capacity times voltage, and you can try to optimize one or both. Voltage typically gets you in trouble because of stability. Infinite power, lasts forever, safe, and costs nothing, right? So those are our design criteria. And so in order to achieve that, what do we need? We need an understanding of materials and architectures, as both George and Stan were talking about. Are we married to inorganic systems? I hope not. Do we need crystalline structures? I hope not either. So we need to go beyond what has been traditionally the realm of batteries, which is basically metal oxides and solid state materials, and try to go beyond that. Understanding structure and composition as well as dimensionality. We talk a lot about nano. Is nano good, better, or worse? We still have not defined that. We try to stay within a regime where we can take crystal structures, but that's really no reason to stay with a particular length scale. And clearly we need to understand the interfaces involved, solvent electrolyte interfaces as well as transport. Remember that both electronic and ionic transport dynamics are involved at the same time in the same volume of space in all of these materials. We need to develop this idea of operando characterization tools. I'll have a little bit of that in a second. Integrated efforts, meaning experimentalists, theory, and engineering, as well as workforce development. And so some of the challenges, understanding electrolyte effects in the batteries, I think we're beginning to understand that, as George was mentioning, going from sort of the atomic and molecular. What controls ionic and electronic transport, the proverbial solid electrolyte interface formation. How do we control in a deliberate fashion composition and morphology, especially given that it's sort of an irreversible process. So it's very hard, to turn around. Can we make any metal anode safe and work? A lot of talk about lithium metal. I've yet to see anything that we can actually be reliable. Multi-electron materials. So we go back to the idea of energy, which is a part of a capacity and voltage. Are there any alternative mechanisms for charge storage? And can we enable high energy water-based batteries in some sense, taking a page from the folks at the Army Research Labs and the watering salt approaches. And we need to really train the next generation of electrochemists rigorously so that we don't hear comments like, we observe a large overpotential and we think it's mostly kinetic. Are you kidding me? It's all kinetic. That's why we call it an overpotential. Or that we can calculate a thermodynamic overpotential, right? You can calculate barriers, but there's no such thing as a thermodynamic overpotential. So here I include a little bit on the sort of operando methods. So here on the left, this is lithium metal growth. This is on X-rays. We can also now these days do operando X-ray diffraction. This is some work by my group in copper sulfide. More recently, for lithium sulfur, we can now do imaging with confocal Raman, looking at different stages of the lithium sulfur batteries, be it the polysulfides or elemental sulfur. DEMS that can provide a lot of information about degradation mechanisms. Here's one in organic materials with performance metrics. This is 500 cycles at 5C with tremendous capacities. I mean, this rivals just about any inorganic system. Can we make these systems maybe a little bit dense and slightly more stable? And then the idea also of going through the architectures, meaning can we optimize, volume and space to achieve, real applications? This will be very dependent on the application space. This is the group right now. This is self-promotion. This is the Abruña fashion statement. These are the folks who brought home the bacon, in particular DOE, NSF, and a few industrial folks. And of course, we have to recognize, people who brought us here. So here's John, Stan, and Akira. I had the great pleasure of presenting this to Stan back in November. This is from a local artist, Alice Molbach. Thanks to Jordi. And I'm done according to my 5 minutes and 5 seconds.
Thank you, Tito. Okay, Claire, you're up.
So the good thing about being last is that I can whiz through all the comments made by everybody else. So I just wanted to start by reminding people of the points that have already been made, that we need to think about sustainable batteries. And of course, cobalt's an issue, but now we're moving towards nickel-based EVs, and nickel is now becoming one of the elements that we really need to consider. But we also need to think about how we make a battery in such that the whole production of the battery reduces the CO2 emissions. And so the whole life cycle needs to be considered. So I just wanted to reflect on a few ways of making cheaper batteries, because I think that helps to sort of think about the science that we need to work on. So obviously the obvious one, if you want to make a cheaper battery, use a cheaper material. That has materials implications, but there's sort of other ones that make batteries cheaper. One of them, of course, is to increase energy density, and we need to do that safely. We can do things that are simple, like make thicker electrodes. And what that means for the sort of material scientists and the chemists out there is, how do you design structures where you can move ions and electrons as fast over thicker structures? And this is a non-trivial exercise, and you need to be able to make these heterostructures or designed electrodes from the bottom up to reduce price. So I think there's a lot of fundamental work that one can think about to sort of the science of creating thick structures that allow you to have a battery that's going to be big enough for storage on the grid. And this is just a sort of illustration of the challenge. The UK hydro, there's 2 hydro plants in the UK, and one is this mountain, the Norvik, where they dug the whole mountain out and use it to pump water and up and down, and that gives you 9.1 gigawatt. And the Tesla Australian battery is in the same unit, but it's still an order of magnitude out. So we have to make big batteries. So I think the other point that people have made and touched on is that we're so close to the theoretical limits in terms of energy density that we really need some radical new approaches. And I think in terms of the students in the audience in the UK, we're here with the sort of 2050 agenda. So it's about doing the fundamental science now that is going to really change the field in the next 10 to 20 to 30 years. So how am I going to suggest you do it? First of all, I'm going to suggest a laptop that works better than mine. In the UK, there's a new institution. We're all plugging our own ones. This is the UK one. It's called the Faraday Institution. I lead one on battery degradation, where there's a lot of development of new tools and in situ metrology to really understand how the batteries degrade. I can talk more about that later on, but I just wanted to sort of talk more about some suggestions moving forward. So Tito talked about the SEI and the problems of designing structures that inherently are in one direction. But I think we could sort of raise that challenge to the next level and think about, how do you control metastable materials that are always operating under non-equilibrium conditions? You know, how do we design pathways where we can get to choose the direction something takes? So Tito made a offhand comment about those of us who've dared to say that an overpotential might even be thermodynamic. And of course, we know that the overpotential is not thermodynamic, but we know that there are pathways that metastable structures can take, which can be dictated by how you set the voltage. And I think we need to move to the position where we really are able to uniquely position atoms, control them, and then we need to in order to do that, we're going to have to develop much better ways of understanding interfaces and new tools. Okay, we can talk a lot more about moving beyond lithium. We all, particularly in your neck of the woods, you've a lot of work on that. I just want to sort of reflect a bit more on paradigm shifting technologies. And of course, the lithium air battery stands out there as the sort of elusive one. And I know that some would feel that it's not necessarily on the roadmap, but I'm going to argue that actually we need to think about processes that happen in the solid and the liquid, and how we interface redox processes that are based in liquids and solids. And I think the use of redox mediators in lithium air is a nice illustration, where you can take, for example, a quinone, you can oxidize the quinone, you can get that to reactive oxygen, and you can control where you deposit the solid product, in this case, the lithium peroxide, or in some case, the lithium hydroxide. And then you can get another redox mediator and you can flow that in to remove the product. And so this then leads me on to the sort of really thinking outside the box. And I know this is maybe controversial, but I think we have to embrace redox flow batteries. And what I mean about embracing the redox flow battery is getting rid of the concept that the battery is confined by the box. So in the traditional lithium ion battery or any sort of standard battery, all of the energy density is in a fixed box, and that dictates how much capacity you get out. Of course, in a redox flow battery, you can flow things in when you want them. And there are challenges. These batteries are no cheaper at the moment than lithium ion batteries, but it's that sort of ability to think about different fuels and fuel mixtures that I think gives us a potential to do something radically different, and to sort of think about ways that fuel cells and batteries can come together to make much bigger battery systems. And this is just some examples of some NMR methodology we've been developing to watch flow systems on the fly. And then, of course, we need to design new materials for high rate. The fact that there's so many rapidly emerging markets for batteries means that there's space for new chemistries and allows us to explore different things. We need to reflect on when it makes sense to combine batteries with other technologies. There are people trying to do solar-based batteries. Does that make sense? Or does the sunlight and the heat result in too much degradation? And then, of course, we can dream about putting fibers into batteries that will allow us to monitor things on the fly, connect with GPS, do big learning, machine learning, and solve things as we're driving along. And then the solid state battery system, just that's something to reflect on. So just sort of end, I hope as a chemist that the battery market is growing so fast that there's room for lots of different chemistries, but growth has to be sustainable. And we need to design our batteries up front so that they can be recycled. And that may come with compromises in how they're put together. But if we can design them to be pulled apart more easily, that will reduce cost. And so just to final, I think the aim is to understand non-equilibrium processes and metastable materials and to mitigate degradation. Thank you very much. I think I'm way under my time. I could keep on going.
Thank you, Claire. Okay, so we have all the opening statements. And we can start a discussion. I'm looking at the chat. And we have already a question from the room by Samji. Is Samji allowed? Is he able to ask his question live? Thomas, can we get him to ask him the question? Otherwise, I'll just read what you copied.
Yep. Hold on 1 second.
Samji, why don't you go ahead and ask?
Hi.
Go ahead.
Yeah. So I wanted to kind of. I'm a fourth-year graduate student in chemical engineering at Wayne State University in Detroit. I wanted to know what are your thoughts on moving beyond lithium-ion in terms of lithium air and stuff like that. The one field of lithium air that I feel kind of disconnected with is tuning or tailoring the solid-solid interfacial catalysis part of it. And what are your thoughts on tuning the discharge products in these batteries using some solid catalyst such that you can probably go to LiO2 or Li2O besides Li2O2 and then tune the charge over potentials accordingly?
Claire, you're the one who talked about that. You want to take it on?
Yep, I'll do it. I mean, I think that I talked more about the use of liquid redox mediators. I intrinsically, when tasked to take on this workshop, I'm sort of thinking about the long term, not the short term. I intrinsically think that a solid catalyst gets covered with junk. And so if you're going to use the solid catalyst, you've got to couple it with a liquid one. And I feel like lithium air is such a difficult problem that you can't just sort of do a simple thing like take a manganese oxide catalyst. The catalysts to date have been, the solid ones like the manganese and the rutheniums have been shown to be much better at catalyzing electrolyte degradation and catalyzing the things that you want them to do. So I personally think that we have to solve this problem. We've got to get OER and OR to work in this field because it has impact not just in lithium air, but it has impact on so many other electrochemical issues that the advances in lithium air have impact in so many other areas. So I'm personally not pushing the solid at the moment, but I think maybe coupled together with an appropriate redox mediator, you have a chance of doing it. But also remember that if you're going to move towards a lithium oxygen versus, lithium oxide versus peroxide, you've got to make sure the voltage windows are right for that formation thing. So you may involve having to move to different electrolytes as well.
Okay,
Jordy,
thank you.
Go ahead.
Can I make a comment on that?
Oh, yeah, yeah.
So,
I mean, if you want.
Claire talked about the various kinds of catalysts. There are some solid catalysts that look interesting. One of them is moly disulfide. It's a two-dimensional material. And at the edge of the two-dimensional material, the exposed moly atoms, if you have exposed moly atoms, and of course you have to make the edge, make sure that you do have moly there and not sulfur. But those orbitals are actually quite good catalysts for the lithium-oxygen reaction. And there was a sort of a test battery made, actually it was done at UIC by a colleague of Jordy and mine, Amin Salehi Kojin. It's published a couple of years ago in Nature. A battery that went more than 500 cycles. And that's quite unusual for lithium oxygen. I mean, the typical lithium oxygen battery might go 20 cycles, or really a very good one might go 50 cycles. This went hundreds of cycles. So there's something there. And it was the first time this catalyst had been tried. The moly disulfide is very interesting in that the edge is the catalyst. And once the lithium oxygen compound is formed, the discharge compound, it migrates to the flat surface of the moly disulfide and can be stored there. So it does two functions. This battery also happened to have an ionic liquid as the electrolyte, can be rather expensive, and we're not there yet, but quite an interesting breakthrough. And I think this is the kind of thing that we should be looking for in the R&D field. Where are the new ideas? And where are things that are holding promise? We don't have to solve every problem, but we solve them one by one, and eventually we'll get to the end.
So just to add on this, one last question. Do you think young scientists like me who want to pursue careers in these fields in the future is looking at the solid-solid interfacial catalysis in terms of solid lithium oxygen species being formed on a solid catalyst? Is that a future career path that we can aspire for?
Can I comment on that? I mean, I always think you have to ask yourself, in terms of developing a future career path, what are you going to do that's new, and what is the fundamental question you're going to solve? You know, I don't think your future career path should be based on one interface. It should be, you know, what are you trying to learn that moves beyond into different systems? So, and what is the unique insight that you have on that thing? So I would turn that question around slightly in terms of how you think about your future career.
Okay.
Because, you know, by the time you've got a lab, the world's moved on, there are different questions. It's like, what is it that is unique and your angle on that field? And what's transferable to other issues, to other fields?
So if I translate that, if I paraphrase and do the shameless plug of the program, you want to think about problems that cut across, you know, electrochemistry more than solving a specific technology.
Exactly. You know, that could be one illustration of your particular approach and your angle, but, you know, it has to be a sort of broader theme that you're trying to study.
Yeah, what question do you want answers to? And then that defines what you're going to try to do. I also had a comment on the lithium air, and that is, you know, carbonate can be a real showstopper, because you can precipitate carbonate, and it, you know, you have then all of the problems of alkaline fuel cells in addition to the redox chemistry of lithium. So it's really a tough cookie. And I don't know how many, you know, I mean, it was the rage many years ago, or a number of years ago. I don't think there's that many people working these days on lithium air. I defer to Stan for the wisdom on that one.
You're muted, Stan.
Well, it's better to be muted about when Stan talks about
lithium air.
No, let me just say on lithium air, I think this is where there's been a lot of hype by some rather high-level people. On lithium air, we really need to understand the air process, not necessarily the lithium air battery. Do the fundamental understanding. Don't peddle it as the next great breakthrough in batteries. And this is my concern about a lot of the battery research. People are doing research and selling it on as a next generation battery, rather than I want to do really good understanding of the overpotential or how these reactions actually occur. So I'd encourage all the students in the audience, really look at the fundamental science, because that will then go beyond lithium, go into fuel cells and a whole lot of other areas, whatever area you choose. Don't focus on one thing. And there's too many people in the field now, I think, getting a little bit tired of, this is the next great thing. We need really fundamental understanding to be done.
And there's a very vast literature of those reactions from the fuel cell community, you know, both in acid and in base. In this case, it will be alkaline because of the nature of the lithium air. But that's a field that I think are very active. But really, I agree with Stan that we need to really understand the fundamentals of, you know, oxygen reduction, oxygen evolution in alkaline media, regardless of whether you make a battery of it or not, because it'll tell you which directions to do the research.
You know, I'm thinking of harping in on the idea, since, you know, it's come up from Stan a couple of times, the idea of the hype in the field of energy storage, because it's something that, you know, it's a very hot field still. There was a question by Aditya that he sent up front. So I'm gonna try to give him the floor. And Aditya, you can go ahead and ask. Let's see if I can. Oh no, I think Thomas has to do this. Thomas, are you connected, and are you able to give him privileges to Aditya? Oh, there you go. Go ahead and ask your question. It was, your question about publishing. It's related to what we just got as a question, but go ahead and throw it out and let's discuss from there.
Okay, thank you for this opportunity and thank you for the panelists for giving this discussion. So my question here is, we've been seeing a lot of impactful work being done in electrochemistry, and my way of looking at it is like, when we are exploring this research as a PhD candidate myself, I have to look at how people are organizing their work, how they're doing it. I see that all the very important major work has at least more than 5 authors contributing to a certain amount of work. And so my question is, what strategies you would recommend for someone who has not as many resources, like limited resources or manpower, say a new professor, to publish on par with such a high impact work?
Yeah, so I'm gonna just skate in and build on that to connect to the issue of hype, because I think that underlying in Aditya's question is this pressure that the new generations really feel to publish high impact work, and that's what leads to the wrong incentive that Stan was trying to highlight of the hype, right? So, what advice do you have in a competitive field like the battery field for young people that are being bombarded with the need to publish high impact work, which then needs to be hyped, which then leads to the old schoolers saying, why are you hyping your work?
Maybe I'll address that first. I would say most of the highest impact work these days is not done by an individual. So most of us on this call today are in large teams. So if you're a synthetic chemist, you're going to interact with a theoretical person, probably with a characterization expert. So I would say to any young assistant professor, build collaborations, find folks you can work with, and work from there. As we mentioned earlier, make sure it's fundamental science. And don't be worried about working across national boundaries if that's easiest. It's quite often easier to work with a colleague if you're a chemist with a physicist in a different campus. But, go ahead and build those collaborations, and it helps your students. They'll learn theory and experiment by working with others. And I think everybody on this call is either associated with an Energy Frontier Research Center or with a hub like JCESA, where we all work as teams. And I think that's the future approach. And one beef I have is don't always try to publish in high impact journals. I know all the students demand that. But I remind folks that the two Nobel Prizes IBM won in Switzerland are probably in second or third rate journals, not in the top journals in the field. You don't have to publish in JACS, Nature, and so on all the time.
But Stan, you use the word second rate. You should just say solid fundamental journals, not second. There's nothing second rate about them.
Second tier is what I meant.
They're specialized journals. That's the euphemism, right?
Yes.
I mean, there's also the sense that the more expensive the instrument, the better the data, which is complete nonsense.
Right.
Yeah, just because you use, a high-powered TEM or a synchrotron does not make the data any better. You can, you can get good data with those instruments. You can get lousy data with those instruments.
So how do you go about that? How do you, what do you, what does it mean, good data? Can you elaborate on that?
I mean, the fact that you use an expensive instrument doesn't, you can do a lousy, measurement with a top of the line TEM, right? But because you did it in that instrument, then of course it's gotta be right. No. And you can actually do very fundamental high quality work with basically a potentiostat. And that's a lot less expensive.
And I think it's worth pointing out, everybody in this last 3 months have had opportunity of designing the smart experiment. We've had lots of time to think about the experiment and not rushing in the lab and doing every experiment.
Yep. And that's again to the young guy. The standard question I ask my students before, the most inefficient use of your time is in the lab. Make sure that any experiment you do is worth doing and why you're doing it. If you cannot articulate that in 30 seconds, think about it.
This kind of goes back to what Claire was saying before about thinking about,
Yes.
articulating the question properly, right? And I saw that you raised your hand, so go ahead, Claire.
Yeah, I was just going to say, I mean, I hear what you're saying, and I think it's a real challenge for particularly the junior people to have the confidence to say that my work will be recognized if I continue to publish in, the strong, solid journals. I think there may be things that you can do is to make sure that to have the guts to publish in the Journal of Physical Chemistries, the JESs, but then maybe make sure that you're giving clear talks where you're articulating what your contributions are. Or, I mean, there are too many review articles in this world, but still make sure you're writing good introductions where you've pulled out the essence and the nuggets and the hypotheses of what you're doing. And then gradually it does get recognized. But and having the guts to be clear and presenting things does help. But it's a challenge, and I think we, at all levels, need to be fighting when we evaluate people. And I'm going to sort of challenge even the junior people to think about when they look at people's CVs for postdocs. How are they making those evaluations? And that's, at all levels, we have to make sure that we're looking for people who may be in interdisciplinary areas or not coming across in sort of in the traditional boundaries, and making sure we give enough time to hear people to understand where they're coming from. So I think it's a real challenge, but I think we have to be very cognizant about it and think about when we interview people, are they, especially if they're coming from a different background, and trying to sort of find different ways of seeing excellence in people.
So you're basically saying that they have to play the long game, which is, right?
Well, I think you have to have the guts in what you're doing. I mean, science is full of sending papers out and things that get rejected, but ultimately you have to sort of have confidence in yourself and make sure you're clear on what you're trying to do, and there are clear hypotheses behind the science you're doing.
Yeah,
So, Jordi, can I chime in on that one?
Go ahead.
And I would agree with everything that Claire and Stan and Tito have said. And my experience is the more you know, the better off you are. So as a young scientist, you should be looking for collaborations. I think that's exactly right. As Stan said, you got to make the relationships in the community, and you want to make them, as Claire said, with the right people, not just anybody that comes along, but people that you've selected yourself, filtered, that you think are, high quality. And this pays off. So you'll learn something on every paper that you write with all your collaborators. And after you've written 10, 100 papers, you get really good at it. And you don't get good at it by sitting in a corner. You get good at it by doing it. It's a lot like playing the piano. You practice the piano and you can't play. And so you keep practicing, and one day you can play the piano. And you say to yourself, what happened? It's hard to know what happened, but you practiced. And it's the same with writing papers. It's the same with collecting or selecting colleagues. And I think you start with the best intentions. You don't lower your standards. And it takes a bit of time, but it happens.
Can I just come back on that? Just speaking as someone who's just had a paper rejected during this webinar. I was told it's a nice solid piece of work, but not suitable for a high impact journal.
Oh, there you are.
You wanna, this is gonna be shared on YouTube. Do you wanna, put the editor on the spot?
I can share it with you. But so, I mean, one practical suggestion I've had when dealing with this at the moment is to put things on the archive and to think about ways of getting your work out, while you're going through this sort of rather depressing process of people. And I think the archive is just giving a different forum for discussions. And so I applaud JACS for having done that in chemistry. And of course, it's been in there for materials and physics for many years. Anyway, it's just an idea. And I just wanted to say that even the Clares of this world get their papers rejected.
It's part of the game.
Yeah, one more comment. When Al Bard was editor of JACS many years ago, he had one editorial that was entitled something to the effect of the smallest publishable unit. And at the time it was, if you have a piece of work, how many ways can you cut it to increase the number of papers you have in your CV? It's a really interesting read because it really addresses some of these issues as well. And so you have, you know, people with sort of pathology, you know, 1,200 publications, you know. Are you kidding me? You know, by the time I get 1,000 papers, I think I'll be about 190 years old.
Just for the record, this paper was 30 pages long, Tito, and it was still rejected.
Okay, so I'm going to diverge us back to some of the issues that you raised in terms of the scientific questions of specific to batteries. And I want to bring to the floor Daniele. I'm hoping I'm not butchering the name. Thomas, yeah, okay. Go ahead and ask your question because it'll be a lead into a couple of things that I've seen flying by. You need to unmute yourself. Uh-oh.
Maybe we can come back to Daniele.
Well, I can also read the question. We can't hear you, so maybe that the microphone is not working. So I'm going to read it for you just for in the interest of. This was a question for you, Claire, and I'm going to paraphrase it. You talked about flow batteries, you know, rethinking the battery. And the question was, do you really think that they're going to be competitive in the automotive sector? And more specifically, improving, you know, the power density and what are the improvements that are going to be needed for that. This connects to something that Jeff also talks about, which is moving, you know, the eternal question of moving beyond lithium ion. And so flow cells are one of the things that are thought about for beyond lithium ion. You know, what were you thinking about when you were putting that forth in terms of rethinking the battery architecture? So in terms of these two questions.
Yeah. So, I mean, first of all, I was sort of thinking about not the short term, that is the long term agenda. I suspect that they're not going to be suitable for cars and the automotive sector, but I think it's in grid applications. And I suppose I was thinking about the fact that it allows you to be much more fuel diverse with organics and quinones and just the idea of being able to produce more recyclable, sustainable materials and flow them in and move towards something where, I mean, a redox flow battery is just a fuel cell, except it's reversible. And I just think ultimately there's no way you can scale a battery that I mean, okay, maybe it's controversial, but I just don't see how you could make a battery design based on single cells that's ever going to be the size of a mountain. And on contrast, a vat of liquid that's the size of a lake potentially does it. Yes, there are challenges, but I think the diversity of fuels that it allows you to think about means it has to be worth doing. I don't have any ideas, but I'm just telling you I just think that's where, you know, the next generation of people in this room should be thinking about trying to do it, where the people who've been trained by the Titos of this world that organic is best should be looking for the new molecules.
Question on that, Claire. When you say new fuels, you mean redox couples? Is that what you mean by fuels?
Yeah. I mean,
okay.
Well, what is a fuel?
You know, yeah, okay.
I mean, a fuel is something you combine together to produce, but in the flow. So, I mean, the only thing that's stopping a quinone-based system working is the degradation. So the only thing that's stopping vanadium, I mean, the vanadium systems are not working because they're still too expensive. There are manganese chemistries out there, but still there hasn't been an ideal manganese-based compound that is highly soluble enough.
Yeah, the energy density is always compromised. Yeah.
It is, the energy density is always compromised, but we're going to have to make compromises.
Yeah. Oh, yeah.
And I mean, one of the things that I'm quite interested in, and tell me it's bonkers, but Jordy said I was allowed to say things that were bonkers.
Yes.
You think about a lithium air battery and you think about all of its problems, but what you want on the grid is a lot of stored capacity so that you just use it when there's no wind. So you have lithium metal sitting there. You turn it on and you flow the liquid in and you have your lithium air battery because you've got enough oxygen there. I mean, the oxygen's sitting there waiting for you in the air. And then you shut the system off so you don't get the long-term degradation. And then you've got, even in Hector's nice background, time for it to charge, whether it's coupled to your solar system. So if you start thinking about the different applications, you realize that there are some technologies that get automatically dismissed if you're thinking along an electric vehicle mode. If you're thinking about grids and microgrids, then that charge-discharge cycle is different. So again, I could be completely barking up the wrong tree, but I think thinking about how you charge and discharge in the grid space may mean there are different chemistries out there. And I feel like we have no choice but to think bigger, because we have to do this at the 20, I mean, in the UK, 0 carbon by 2050 means everything is electric. So, we're not going to get there unless you think outside the box. And maybe I suggest things that are completely wacko, but there's got to be a few more wacko ideas out there to make progress.
No, I agree that the grid is, the automotive and grid constraints are very different, and we have to approach it from that perspective. Sorry, Stan.
Yeah, I was going to add, Claire, what you're talking about turning on and off, that's called pumped hydro.
Yeah, but Stan, there isn't enough place. There is not enough pumped hydro in locations.
I was discussing with somebody in Europe just last week, and they're talking about putting new pumped hydro in, because that's the only way to couple with renewable for the difference in demand between summer and spring. But getting back to technology, I think Redox cells.
Stan. I mean, I agree with you that the pumped hydro will always win, but I don't think we can afford to say that to the next generations of students we have made decisions.
No.
They should be in there coming up with smart ideas to change the thinking so that we have different paths moving forward.
Right. I don't disagree. I was going to say, for flow batteries, we have another option you don't have with lithium ion, and that's bipolar technology design. So we can build up a stack that can have 100 volts or so. And I think that's a big plus over standard lithium ion.
Yep.
Well, and if I can comment, talking about wacky ideas, Claire, there's lots of organic compounds out there that we just haven't explored yet. There's about 20 or 30 that we turn to all the time, first things that come to your mind. But active redox organic molecules is a wide open white space. We need to use our computers very effectively in order to scan that space before we do it in the lab. Not enough time for an army of graduate students spending a lifetime and never getting their PhD. That's what it would take to explore that space. Let the computer do it, and find ways to let machine learning even accelerate that screening activity. But there are lots of things out there, and there are some compounds waiting to be discovered that would just be perfect in the flow battery. And I agree with you, and I think everybody, all the panelists would probably agree with this, that flow batteries have enormous potential, which is yet untapped. And it just needs to be tapped.
And just going back to that earlier point about how do you make an impact in this very busy field, in a sense, you've got to have the guts to propose something different. You're going in and saying, I want to look at 811, even though I work on 811 myself, or it's not going to get you the faculty job. It's about doing something, having good ideas about something a little bit more revolutionary, or making up new techniques to do something different.
Yeah, you have to learn to be creative. And I think we don't know that when we start our PhDs. Maybe we are, some of us are a little bit more innately creative than others, but it's a skill. Where's the opportunity?
Yeah, I like, I guess somebody can now run away and say, well, I'm going to be creative by making a lake battery. I like the idea of using a lake as your battery. So that brings us to another, related topic that has come up. If you think of the lake battery as the example, all of you have mentioned in different ways the issue of scale. Atoms to devices has come up a few times. Clare, you talked about making thicker electrodes in connection with the idea of flow cells that allow you to go to bigger scales. So let me put something out there in terms of how does that change the questions? In other words, do you feel like there are scientific questions that the attendee should explore that depend on the length scale or the size of the device that they're targeting, right? Or is it all, if you solve the question at the atomic level, it doesn't matter what the atomic level is, you still get the right answer when you get to the lake battery?
But you kind of know the answer to that one, Jordi.
But I'm the moderator.
I
what do you
mean,
think?
Yeah, go for it.
Well, I mean, I was just going to say one simple, of course, the answer is you can't just scale things up because you have a finite conductivity, electronic or ionic, and the only way that you can get bigger is to get materials that have higher ionic conductivity or possibly electronic one. But you've got to also think about how you design and how you put materials together, moving beyond sort of simple slurry processes. And you've got to do more modeling. I mean, one of the biggest challenges in theory is to how you move from the atomistic through to the continuum level with the same granularity all the way through. And I think that's one of the biggest sort of challenges and how you do that and couple with experiments. I think it's kind of a very exciting area. I mean, I don't have the answers to this question, but obviously the lake battery is very different from the atomic one, and we can't just get bigger atoms.
I mean, I think also we need to start conversations with our colleagues in chemical engineering, which we typically don't.
Yeah. Yeah.
I mean, those people, I mean, that's their bread and butter, figuring out how to do these things. But I mean, we rarely engage those people.
But can I say there's two ways to approach a given problem? Let's say the battery problem. You can play around. One of them is Thomas Edison, who just tried everything until he found something that worked. And when he found something that worked, he didn't really care why it worked. He knew it worked and he went with it. He made a company out of it. The other way is to do what we're doing now, go from the bottom up. Understand the atomic and molecular level phenomena, and then design on the first try, not the 10,000th try, but on the first try, design something that works. And that is starting to be possible now. And I think I have enormous respect for Thomas Edison. I mean, you couldn't do it in his day and he did the right thing. Well, it's a little different now. And, let's get a little bit more real.
Yeah, on the topic of architecturing, Thomas, can you give the floor to Mang Chen? Because he had a question on that too, and maybe he can articulate it. Go ahead. You're going to have to unmute yourself. Hopefully your microphone works. Oh.
Got shy at the last minute.
Oh, no, you're unmuted. Go ahead. Oh. Okay, it doesn't seem like his microphone is unmuted, but it doesn't seem like we're hearing him. So he had a question about, connected to the toxicity issue, moving away from, going more towards sustainability. And he was asking whether you could take, old school materials that are non-toxic. He was putting the example of lithium iron phosphate, but one could think about manganese oxide, and just change the architecture. and you just rethink the way that the battery is put together, could that allow us to squeeze a little more juice out of more old school materials? And this connects to, you were talking, Claire, about the slurry process and, rethinking that too. Are we pinned to that architecturing? So, do you see architecturing opportunities, or have we tried them all already and you're going to tell the students that are in the audience, don't bother because we tried everything?
I don't think I should be the one who should answer that one. I think Stan should try that, and then I'll come back at it.
Now, he mentions LFP, and I think LFP still has a lot of opportunities. No reason why LFP shouldn't be the cathode of choice for most grid if you're going to use lithium ion. You don't go to Redox. There's no reason to use cobalt. But it brings up how do you make LFP low cost? Because right now, LFP costs almost as much as the NMC materials to make. Because you have to make it ferrous, you have to coat it with carbon and so on. There's not enough research in the synthetic approaches that can be scaled up to large scale. So I think no. LFP is certainly a material of the future. I think BYD is the world's expert on it outside of Yet-Ming Chang. And you can play games with LFP, put some manganese in there, go from 3.5 to 4 volts. So you can tune it a bit. But don't give up hope on these slightly lower energy density materials that might be safer and much lower cost. And I think BASF and others are trying to make manganese oxide work for lithium ion, because manganese is clearly lower cost. There's much more manganese, and no nickel, no cobalt. But there's some issues there. We need to fundamentally understand why manganese and lithium tend to disorder when you make batteries out of it. So there's lots of fundamental understanding to do that.
I mean, I would also add to Stan's comments that it goes back to, the role of what we are doing in universities and national labs versus industry. I mean, I would, and this might be seen as controversial, but I would urge people not to do the sort of D work, but rather doing the R work. And if there's a genuine, getting manganese oxides to work requires understanding yarn-teller distortions, understanding why manganese migrates and when manganese migrates. So again, if you're looking at manganese oxides because you're trying to sort of unpick why it doesn't work, that's great. But I would say subtle tweaking wouldn't be what one should be trying to do. I think there's been enough work on, yet another graphene coated nanostructure of something, but more, what are the fundamental things that you're trying to do in terms of electrode structuring? I mean, if intrinsically something is going to dissolve, however much you put a coating around it, unless you have an application where you only need 20 cycles and you can justify it, but then if you're going to have to do that, articulate again why you're trying to do it.
It's interesting that you just mentioned graphene as a hyped material, because Simon was asking about graphene as a buzzword, or does it have an actual future in the battery space? Do you see that? Do you see these kinds of carbon nanomaterials that come and go as an opportunity for perhaps architecturing, scaffolding? Some people say that you could build 3-dimensional structures with these carbon structures.
Well, okay, I sort of jump in the deep end with a sort of a noose around, stones around my feet at some point. I mean, graphene's an interesting material. It's a carbon, and batteries have carbons in them. I think it has a role in thinking about electrode structuring in terms of porous electrodes, where its high surface areas could allow you to do things. I think that academically, electrode structuring, creating hierarchical structures in a controlled way is an important field. I mean, I think if we look at where nanoscience was 20, 30 years ago, people had to learn the rules to make nanoparticles of different shapes and facets. And now we almost take that for granted, that if we want a cube or a rod, you know, we can do that. We can do two rods and different shapes in aqueous solutions, but we can't actually do that in non-equivalent high temperature modes. We can't do complex oxides. So I think if you can again say, you know, I'm taking hierarchical architecturing to the next level, then it sort of makes sense. If you're starting to learn the rules, then I can sort of see it as a valuable contribution. I think graphene does have a role, and why it sort of works to a degree in the silicon space is that it is providing this stable surface to form an SEI on. So again, thinking about why it's useful, as opposed to it just being, you know, I put graphene in and it's working, but actually what is it about that structure that is actually giving you a slightly improved performance? And what else do I need to know and do?
Tito unmuted himself. Did you want to say something, Tito?
No, I was going to say that, I mean, it's a known fact that if you put graphene in your cereal, you'll grow taller, younger, and more handsome. I think it's overblown. And also the cost, you know, large scale, I mean, that to me is a non-starter. I mean, you can learn something about architectures, as Claire was saying, but to pretend that you're going to make, you know, ginormous amounts of material based on graphene, I think is not being realistic. And this goes back to the hype of Stan, you know, he said, well, I put graphene in my battery, you know, I can squeeze out 3% more, you know, 0.2 C, you know. I think we need to get beyond that. I mean, it's an interesting material, has a lot of interesting chemistry and physics. It's a different thing when you put it, you know, in really large scale manufacturing at cost competitive, conditions.
We're kind of coming full circle, and we're toward the end of the allotted time. I'm gonna try to get that one last question, and then we can see, you know, how much longer you want to go. But talking about the hype and going back to the hype, and then a point that Tito raised about the rigor in training people. Michael Gerhard, I hope I didn't butcher that either, had a question about the educational aspect of electrochemistry, and I wanted to give him the floor because I think it's an interesting one. Okay, hopefully he works.
Hopefully I work. Can you hear me?
Yeah, you're good.
Excellent. Yeah, so thanks for giving me the opportunity to ask a question. It's been an interesting panel so far. My question is really about how can we improve the teaching of electrochemistry as it relates to all these interdisciplinary areas that we've been talking about today in energy storage. You know, what the kind of specifically what I was wondering is, should we be trying to fit it into like a specific department or teach it standalone, or like what other ideas do you have to improve the teaching?
Yeah. Take it on.
Well, Hector, you started it, so you should start.
Well, okay, so if you, at least in the US, if you look at how many departments at the graduate level offer what I would consider a rigorous course in electrochemistry, is very few, very, very few. And now because batteries and fuel cells are popular items, you have a lot of practitioners who come from very different backgrounds. And in some cases, you get these people talking amongst themselves. They say things that if my students told me, I would say, don't let the door hit you on the butt and don't come back. But you hear it enough times and they think of it that is being correct. And that is a huge disservice. And in particular, I think part of this was that, let's say about, I don't know, 30 years ago, research in electrochemistry was extremely difficult to support. And students are not stupid. You know, they see people having a struggle getting funding and says, I'm going to do something else. Now, you know, it's a much more, you know, let's say attractive discipline, but now the people who used to teach those courses are either retired or dead. And for, you know, in that sense, you know, a dinosaur of that generation, one of the few places I think here in the States that offers such things. But we need to really engage, you know, the new generation. I think there's a lost generation. I think the newest one is coming back on it. But after my generation, I think there was a lost one there. And those are the people who will be in sort of leadership positions now. But I mean, we could have, you know, like like short courses and stuff like that to get people engaged.
But I mean, speaking as the generation that, you know, managed to get through with very little electrochemistry, it was taught very boringly.
No kidding. No kidding. Yes.
You know, there was little connection between the Nernst equation and anything practical. And, you know, the major excitement was plating copper pennies.
Yep. It's our fault too. I mean, when the exciting thing is potentiometry, oh man, you know.
And so I look back and I sort of see that some of this was there for us, but it just, you know, there was no connection.
Yeah. But if you take the average person doing batteries and says, what is the Sand equation? I bet you they won't know.
Well, I only know because I've done lithium plating.
Any battery, right? Anything that's galvanostatic, you should know what the Sand equation is and what it does, and why, you know, charge discharge curves look the way they do.
But Hector, you should know why you should know. And I think that's where we've been bad at explaining. You know, why should you care about the Sand's equation?
Could it be a problem of, you know, access, in the sense that doing an electrochemical experiment, carrying it out, is actually not that difficult, right? I mean, you know,
it's one of the
stuff together and passing a current to it. So how do we get around that?
That is part of the virtue and the curse, you know, because you can buy potentiometers for not much money. You can do, you know, cyclic voltammetry or current potentiometry without much effort. But understanding the fundamentals of that, what the transport means, you know, that's a whole different level. And when you understand it at that level, then it makes a whole lot more sense. And interpretation becomes not just a guesswork, but actually more deliberately.
But I think we need to be, I mean, you know, I do so little teaching, I'm embarrassed to admit, but we need to make more effort to explain in those first year and second year courses why you should care about the Sand's equation. I mean, and the Nernst equation, why, you know, why that battery is influenced by the Tafel plots, and I mean, or why that's a useful metric. And I don't think we spend a lot of time doing that. And you know, even I mean, it's sort of stuff as a solid state chemist, you know, I would always talk about the Yarn-Teller distortion in the context of lithium manganese oxides and why you can't go to Li2M and 2O4. So trying to sort of integrate that stuff early on into the courses, so then it comes into the graduate level and you have it more part of the curriculum.
No, I mean, as you correctly point out, I mean, the teaching of electrochemistry has not exactly been a strong point of the community. And then when the first edition of Barton Faulkner was in 1980, I believe. And unfortunately, I mean, that first edition was impenetrable. Students hated it because, you know, the math was just, it made most of the concepts inaccessible. I think it's gotten better. But since everybody uses Barton Faulkner, then that also, you know, presents some issues. So you need, in some sense, you know, like,
you need a new book.
There's going to be a new version of Bart Faulkner and White coming out. We'll see how that plays out. Hopefully Henry will inject a little bit more readability to it. I mean, by any measure, it's extremely rigorous, but students get, you know, the math gets a little bit in the way at sometimes. In the interest of being too rigorous, I think you lose the more sort of intuitive sense, you know, that you look at an equation and what is it telling you in terms that you can correlate to an experimental observable.
So I mean, there's the real possibility, at least in chemistry, to do these sort of things, because without being controversial again, you know, physical chemistry is sort of having to redefine what it does.
Oh yeah, yeah.
And there's some, I mean, it's a really exciting area, the whole interfacial processes, you know, understanding electron transfer processes, you know, it was considered 1950s chemistry, but now is critical. I mean, it's something I didn't sort of touch on very briefly on my slides, but sort of understanding how electrons are transferred across interfaces, you know, is still something we know so little about.
Yeah, and even conceptual, you know, things like, is it an inner sphere or outer sphere? Now that, you know, now we can address those things in great detail.
Yeah, and we have just, I mean, all of those sort of questions that were there, you know, now, as you say, we can actually answer those questions and track how fast they happen. And I think if we want to go to high rate batteries, you know, we need to know how fast you get the ion from the solution into the solid, how the electron transfer process occurs, and sort of articulating those sorts of things, I think is really exciting. And doing the measurements even more exciting.
And I mean, experiments like, you know, Henry Tauby, you know, probably before I was born, you know, in this, you know, high spin, low spin, you know, where, you know, I mean, those days, you know, instrumentation was, you know, a Beckman DU and a Bunsen burner. Yet, I mean, those experiments still are as valuable today as they were, you know, 60 years ago. And so it goes back into the idea of thinking, you know, clear thinking in terms of experiments.
Stan, you wanted to say something?
Yeah, I was going to say, no, where electrochemistry has really let us down, it's taught us classical subject, and it doesn't really interface with solid state chemistry, with reacting electrodes. It really addresses electrodes that sit there. Things happen on the surface, but not inside. So I think until electrochemistry involves the solid state chemistry aspect, it tends to turn off students.
Yeah, I mean, the tradition has been to use an unreactive electrode. So if it was reductive, it was mercury. And if it's oxidative, it's carbon. And then the electrode is either a sink or a source of electrons. And I mean, that's really, I mean, things have moved from that, you know, in a very real way. And batteries and fuel cells are examples where the electrode is not just a sink or source, but an intimate partner in reaction dynamics.
So there's an opportunity for a new textbook then, I hear.
Go ahead and write it, dude.
Yeah, right.
It won't be the tenure though.
Sorry,
so yeah, it's an issue of how it's been presented. I completely agree with Claire. I mean, not the most exciting folks. And also, you know, from a student standpoint, you know, you can get excited by going to a laser lab. You see all these things bouncing around. You see a potential stat and say, well, really great, you know. So there's a missing element of how to engage students.
Okay, so we're at 11:40. We said we were going to run until 11:30, so I don't want to take too much of your time. I've already taken 10 extra minutes, and we made up for some of the delays in the beginning. So is there any additional thoughts that you want to put out there before we close, or should we just you know, let you go and do other things that you have to do?
Well, I would say that the interfacial solid-liquid interface and the sort of electron transfer surfaces structure at the interface, you know, remains really one of the sort of unsolved frontiers. That there's so much to be learned there, and there's a lot of opportunity to learn, but also to design how things happen at those interfaces. I mean, at the moment, we're still even in that learning point. We haven't turned the loop around to think about, given what we now know, what could we do better? And we're doing that to a degree, but it's a wide open space, but important to articulate what you're trying to do in it.
Yeah, I'd like to echo, you know, Claire's comment in that also now we have the tools to do that.
Yeah.
I mean, we have, you know, TEM with unprecedented resolution under operating conditions, which to me is almost, you know, miraculous. Computation has gotten very good. It's not just, you know, a perfect crystal, you know, at 0K in vacuum. And so now we can actually address from a computational standpoint what these interfaces look like. And people have gotten very good at doing that. And also have, you know, very clever people. I think for energy in general and electrochemistry as related to that, it's a great time to be in that field.
George, Stan, any parting thoughts?
No, there's plenty of opportunities out there for all the students. No, go and attack them. Enjoy yourself.
I would echo that, and I do think we were talking earlier about how electrochemistry is taught. The atomic and molecular interpretation, cartoon interpretation, here's an atom, here's a molecule. It's in a liquid, what does it do? It's at an interface, how is it connected? Those things we can, as we were saying, we can now answer. So we can actually look with characterization tools and see. And the computation, as you guys were saying, is phenomenal. It's on the cusp. So next 10 years, next 15, 20 years, it's really going to grow and make leaps and bounds of progress, I feel. So good place to be.
Yeah, and just to plug in, and that'll be my closing thought. The panel in the afternoon at 1 p.m. talks about some of these frontiers, because we're going to have half computational people, half experimental people, and we're going to force them to talk to each other. And that's an area where, they've both advanced in parallel really deeply, and now there start to be questions about, have they advanced so far that they don't even talk to each other? And so that's an area that we're going to explore. And, for all the attendees, hopefully you can make it to the afternoon panel too, because you'll hear some of these topics come up again. We're going to leave it here because, like I said, you've been very generous with your time, but we're over 11:30. If the attendees have any questions, you can try to send them to Thomas and me. You can find the email addresses of the panelists as well, so you can send them directly to them. Just introduce yourselves as attendees to NGenE, but feel free to engage them directly if you want. Up to you which way you want to go. But one of the spirits of one of the ideas in NGenE is to make connections between faculty and attendees, and that's much harder to do in this format. So if you go ahead and break that wall and send an email directly to them, that is perfect. You don't need me or Thomas to do that for you if you don't want to.
I would also like to thank Georgie for coordinating all of this. I'm sure, there's a gazillion hours in the background that we're not seeing.
It's mostly been Thomas, and unfortunately he's all stressed out because we haven't been able to get the live stream to work. Turns out that Zoom is having issues this morning. It's like, apparently there's a ton of people complaining that the live streams are not working. And my daughter was actually in a summer school, and she was walking in telling me my Zoom is disconnecting. So so it seems like Zoom has let us down a little bit this morning. But we recorded this, and we're going to put it on the ECS website. They asked us if we could put it there. So, there's going to be a legacy for it. I've been getting texts from people telling me the live stream's not working. So it'll be on a delayed format. It'll be asynchronous, asynchronous learning, but it'll be there. Thank you, Tito, George, Claire, Stan, in the order that I see you in my screen, for sparing your time to share your thoughts. And I hope that this was insightful for everybody that attended and insightful for everybody that watched. And at 1 p.m., we're back with another panel. Thank you, everybody. Thomas, you can close it out whenever you want.
I'm going back to the beach.
Bye. Bye.
Thanks, guys.